So we are given this differential equation and we can immediately see that it's not homogeneous because we have a 4 here, and of course the exponents of the coefficients will be 0 and 0, so this will have a degree of 0, this polynomial. And here we have a degree of 2, polynomial degree of 2, because it's 1, 1, 2. Here it's just 1. So it's a mix of sums of exponents. So it's not really homogeneous. The other thing we want to check is if it's separable. And if you do some factoring, you will realize that it's not separable. It's not separable. The x and the y are quite coupled tightly. So the solution to this problem is to actually do a substitution. Now, if you can't make it separable, then the first thing you're going to do is look for something that you can factor out, even if it's not just one variable. So for example, in this case, what I see is that the x squared, there's a y squared, there's a 2xy. That to me sounds like a perfect square. So I'm going to factor, or rather I'm going to separate the perfect square. So let's just do that. So if I just write that again, that will be dy equals x squared plus 2xy plus y squared. Then you have minus 4x plus y. So I just like factoring the minus 4 because they're the same minus 4, and it's likely we're gonna find something that looks similar to the first one, to the first grouping. So that's why I'm factoring it. Let's just do that. And here we have dx. And we know that this first grouping is actually x plus y squared. And how nice is that? Now, what we have here is, again, a perfect square. Do you see that? This is squared here, and this is a perfect square. So it's of the form x squared minus 2x minus 4x plus 4, right? So actually, this can be written as x plus y, that's the first part, plus 2, or rather minus 2, squared. Look at that. It looks very nice if written this way. And now, we can make a substitution. So, the reason why we can make a substitution is because the thing inside here is just a linear expression. All the exponents are just 1, and the dx and the dy's will therefore be easily computable. So let's show what I mean. Suppose I'm going to make a substitution v equals x plus y minus 2. So that's just everything inside the parentheses. So computing the differentials, we get dv equals dx plus dy, and this is just 0. And this is a very good form, because that means that we can just substitute dy with dv and dx. And this happens because you don't have anything squared or cubed here. That's why you just have dx and dy. If there was something like squared here, then you will have an extra x term. And so that adds some complexity. And let's just do the substitution. I'm going to eliminate the dy bit here. So I'm going to use dv minus dx equals, and this is just v dx. Right? So what we have is that we have dv v dx plus dx. So we have v plus 1 dx, and therefore dv over v plus 1 equals dx. And that integral is not very difficult. That's just v plus 1 equals x plus some constant c sub 1. And then let's replace, or before we do that, let's just do the exponentiation. So if we raise e to the expressions on both sides, we get v plus 1 c e x plus c1 equals, so ec1 e to the x, then this ec1, so if I just do that for a moment, this ec sub 1, that's another constant, and it could just subsume the signs, so you could eliminate the absolute value symbol here. So if we assume that if we have c2 equals plus minus ec to e to the c sub 1, what we get is we can eliminate the absolute value signs, and we get v plus 1 equals c2 e to the x. And now we just have to replace v here with our original variables, x plus y minus 2 plus 1 equals c2 e to the x. And conveniently, we get y equals c2 e to the x minus x and plus 1.